Universe, time, space, galaxies, matter, energy, gravity, stars, light and particles. Imagine that every atom that makes up your body today was, just over 4 billion years ago, floating in a colossal cloud of gas and dust. The solar system, in its most primitive form, was merely a dense stellar nursery, composed mostly of hydrogen and helium. Something, lost in the ages of time, pushed this cloud beyond its equilibrium point, initiating a gravitational collapse that would give rise to everything we know. Evidence preserved in ancient meteorites reveals chemical signatures of iron isotopes that could only have been created in the heart of giant stars exploding as supernovae. This suggests that our system emerged in a cluster of thousands of stars, a turbulent and violent cosmic neighborhood. At the center of this chaos, gravity began to concentrate most of the matter, forming an incandescent sphere. The Sun, a typical yellow dwarf, now holds 99.9% of the mass of the entire system. It is the thermal engine that governs the destinies of all the worlds around it. In its core, the pressure and temperature are so extreme that hydrogen nuclei fuse to form helium, releasing an almost unimaginable amount of energy. Every second, millions of tons of stellar matter are converted into pure radiation. This energy travels for thousands of years through the star's inner layers before being emitted into space as the light that bathes our days. Around this central furnace, the remnants of dust and gas began to clump together into disks, forming the planets. Looking at the current configuration, we might assume that the orbits have always been eternal and stable loops. However, the history of our system is one of continuous and sometimes violent transformation. The inner rocky worlds, such as Mercury, Venus, Earth and Mars, tell stories of pasts we can barely recognize today. Mercury, for example, is a mystery of metal and rock, with a disproportionately large iron core that defies simple theories of planetary formation. It looks like a relic of a colossal impact, or an orbital migration that brought it too close to the scorching heat of the Sun. Venus, often called Earth's twin due to its similar size and composition, hides beneath its thick mantle of sulfuric acid clouds, one of the most hostile environments in the solar system. But it wasn't always this way. Data collected over decades of space missions indicate that, in the distant past, Venus may have been a blue world, covered by oceans of liquid water that persisted for perhaps 2 billion years. Climate models suggest the existence of a habitable planet, very similar to our own, before a rampant greenhouse effect transformed its surface into a desert of crushing pressure and heat capable of melting lead. The water that once filled its basins evaporated and was lost to space, leaving behind a monument to what happens when a world's thermal equilibrium breaks down. Further on, we find Mars, the reddish desert that captures our imagination today. It is a world of extremes, home to the system's largest volcano, Olympus Mons, which rises to 26 kilometers high. Although Mars is now a cold and dry place, its surface is marked by scars from ancient rivers, deltas and basins that tell the story of a planet where water flowed in abundance. The geological evidence is unequivocal. Mars was once a place with a dense atmosphere and conditions that could have supported life as we know it. However, being a smaller planet, it lost its internal heat and its protective magnetic field, allowing the solar wind to sweep through its atmosphere over billions of years. The search for signs of life on Mars is not just a scientific curiosity, but a quest for our own origins. Sophisticated robots now roam its craters, analyzing rocks that may contain biosignatures preserved for ages. In places like the Eridania Basin, it is believed that hydrothermal vents existed similar to those on Earth that may have been the cradle of biology. The geological preservation of Mars is superior to that of Earth in certain aspects, as the planet does not have the tectonic plate cycle that recycles and destroys the oldest rocks in our world. Mars is, therefore, a laboratory frozen in time, guarding secrets from a period when the solar system was a much more vibrant and interconnected place. As we explore these neighbors, we realize that Earth occupies a privileged but not necessarily unique position in its history. The narrative of the solar system is not linear. It is a cycle of worlds entering and leaving habitable zones as the Sun evolves and the planets themselves change. In the distant future, as the Sun becomes brighter and hotter, the regions where liquid water can exist will have shifted to the outer boundaries. Worlds currently frozen and inert, such as the moons of Jupiter and Saturn, may see their first thaw, while the inner rocky planets become burnt relics of their former splendor. Exploring these celestial bodies forces us to confront our own fragility. Venus serves as a warning about the fate of saturated atmospheres, while Mars shows us the consequences of a planet losing its vital breath. Each probe we send, like the Parker solar probe that plunges into the solar corona to understand the behavior of our star, or the rovers that face the 7 minutes of terror to land on Martian soil, is a step towards understanding the mechanics of this great cosmic clock. The Sun's complexity goes beyond what the eyes can see. Its atmosphere, composed of the photosphere, chromosphere, and the mysterious corona, exhibits temperatures that increase as we move away from the surface, a thermal paradox that scientists are still trying to fully unravel. Solar flares and coronal mass ejections launch charged particles into space, interacting with the magnetic fields of planets and creating spectacles like auroras, but also representing challenges for our modern technology. The Sun is not just a constant source of light. It is a dynamic star whose activity cycles directly influence the climate and space safety of the entire system. The transition between small rocky worlds and gas giants is marked by the asteroid belt, a region of cosmic chaos where millions of celestial bodies orbit, prevented from becoming planets by the massive gravitational influence of Jupiter. These fragments are fossils of the solar system's formation, untouched samples of the original chemistry of the proto-solar cloud. Some of these objects, occasionally thrown from their orbits, cross the path of the inner planets, bringing with them both the threat of destruction and the essential ingredients for life, such as water and organic compounds. Observing the cosmos is fundamentally an exercise in humility. Earth, seen from the depths of space, is just a pale blue dot, a tiny fraction in a vast cosmic arena. Human disputes and daily concerns seem insignificant in the face of the time and space scale revealed by astronomy. However, this same scale highlights our responsibility. If we are, as far as we know, the only consciousness capable of observing and understanding these processes, the preservation of our small refuge becomes the most absolute imperative. The journey of exploration is only just beginning. Each new discovery, whether an exoplanet orbiting a distant star or a new analysis of a lunar rock, expands our understanding of how planetary systems form and evolve. The solar system is a place of continuous transformations, where life may have migrated between worlds via meteorites early in history in a process known as panspermia. If Mars and Venus were once habitable, the question of whether or not we are alone becomes even more profound. Why did life flourish here and seemingly fade away elsewhere? The answers may lie hidden in lunar and Martian caves, protected from the harsh radiation of the surface. Speleologists and astronomers now look to the subsurface as the next great frontier in the search for life and the establishment of human settlements. The idea of becoming a multi-planetary civilization is not just a science fiction dream, but a long-term survival strategy in the face of the changing nature of our system. Technological advancements have allowed us to see what was invisible to the pioneers of astronomy. Worlds like Neptune, initially discovered through mathematical calculations before being visually observed, now reveal violent atmospheres with supersonic winds and storms that come and go in a matter of years. The difference in residual heat between similar planets suggests that their formation histories were distinct, marked by collisions and internal processes that we do not yet fully understand. The matter that makes up the Sun, the planets, and ourselves is the result of a nuclear alchemy that occurred billions of years ago. We are stardust trying to understand the very universe of which we are a part. With each cycle of observation and discovery, we reaffirm our connection to this immense and dynamic system. The exploration of the solar system is the story of our search for context, for identity, and for a future in a universe that is at the same time beautiful, diverse, and profoundly mysterious. Sunlight reaching the cloud tops of Venus reveals a world that, at first glance, appears as a beacon of purity in the night sky. However, upon crossing this sulfuric acid barrier, we encounter a geological nightmare. Venus is the most extreme example of how a planet's fate can be sealed by atmospheric processes. With a surface pressure 90 times greater than Earth's, walking on Venus would be comparable to being 900 meters deep in Earth's ocean. The average temperature of 465 degrees Celsius is not merely a climatic detail. It is a sentence that prevents the existence of any liquid water and challenges the integrity of almost all known metals. The mystery of Venus lies in the fact that it and Earth began almost identically. Both have similar sizes, close densities, and were formed in the same region of the protosolar nebula. However, while Earth developed a carbon cycle that acts as a planetary thermostat, Venus lost control. Carbon dioxide, instead of being trapped in carbonate rocks through the cycle of plate tectonics and the presence of oceans, accumulated in the atmosphere. This created an impenetrable thermal blanket. Solar radiation enters, but the heat cannot escape, generating the most extreme greenhouse effect in the solar system. Recent climate modeling studies suggest that Venus may have maintained temperate conditions for billions of years. Imagine a world with blue skies and shallow oceans that lasted until about 700 million years ago. What caused the catastrophic transformation is still the subject of intense debate. Some scientists point to massive simultaneous volcanic eruptions that released such vast amounts of gases that the planet's removal mechanisms were simply overwhelmed. Others suggest that proximity to the Sun made the evaporation of the oceans inevitable, and once the water vapor, which is also a greenhouse gas, reached the upper atmosphere, it was dissociated by ultraviolet light, allowing the hydrogen to escape into space forever. Exploring Venus is one of the most difficult tasks in astronautics. The Soviet probes of the Venera program, the only ones to transmit images of the surface, survived only for very short periods, some for little more than an hour, before being crushed and cooked by the hostile environment. The images they sent back show plains of sharp rocks, illuminated by a diffuse orange light under a perpetually cloudy sky. There are no sharp shadows on Venus. The atmosphere is so dense that light is scattered in all directions, creating an oppressive and uniform brightness. Analysis of Venusian geology reveals a relatively young surface with few records of ancient impact craters. This indicates that, at some point in its history, the planet underwent a global renewal event where lava covered almost the entire surface, erasing traces of its more distant past. This volcanic activity suggests that, although it does not have tectonic plates like Earth's, Venus possesses internal heat release mechanisms that operate episodically and violently. The absence of a strong global magnetic field also contributes to its vulnerability to the solar wind, reinforcing the idea that the planet's interior has cooled or behaves fundamentally differently from Earth's core. The search for life on Venus has shifted its focus from the surface to the clouds. At an altitude of about 50 kilometers, the pressure and temperature conditions are surprisingly similar to those on Earth. There, amidst the cloud layers, some researchers speculate about the possibility of extremophilic microorganisms that could survive in liquid droplets. The controversial detection of phosphine in the Venusian atmosphere years ago rekindled interest in missions that could collect samples from these clouds. Even if phosphine has abiotic explanations, the fact that Venus is chemically active and complex keeps the planet at the center of investigations into its habitability. The comparison between Earth and Venus teaches us about the fragility of our own existence. The balance that allows life on our world depends on an intricate network of interactions between geology, atmosphere, and biology. Venus is the mirror that shows us what happens when one of these pillars collapses. It is a testament to the fact that size and composition do not guarantee a hospitable fate. A planet's position relative to its star sets the initial cards of the game, but it is the evolution of its atmosphere that determines whether the game will continue for billions of years or end in a barren desert. While Venus represents the excess of atmosphere, the asteroid belt offers us a glimpse into primordial matter that never quite formed a complete world. Bodies like Ceres, the largest object in the belt, exhibit signs of geological activity and even the presence of frozen water. Ceres is classified as a dwarf planet, a link between the inner rocky worlds and the outer gas giants. The presence of bright salt deposits in its craters suggests that liquid may have existed within it until recent geological times. This expands our definition of where to look for environments that could support prebiotic chemistry. The gravitational dynamics of the solar system are governed by Jupiter. Its colossal mass acts as a shield, deflecting comets and asteroids that might otherwise strike Earth more frequently. However, Jupiter is also a perturber, whose orbital resonances prevented the formation of a planet between it and Mars. This duality is a constant feature of the cosmos. The same force that protects can be the cause of instability. The system's architecture is not static. The planets migrated from their original positions during the first few million years, in a process described by models such as the Nice model, where gas giants swapped places and launched trillions of objects to the outer edges and into the interior of the system. The exploration of Mars, on the other hand, offers a direct contrast to Venus. If Venus is a hell of pressure and heat, Mars is a desert of cold and vacuum. However, Mars preserves evidence that liquid water was not just a passing phase, but a persistent feature of its surface. Jezero Crater, where the Perseverance rover operates today, is an ancient river delta, a place where water flowed and deposited sediments billions of years ago. The choice of this location was not accidental. Deltas on Earth are excellent at preserving organic matter. By drilling and collecting samples from these rocks, we are searching for the chemical fossils of a biosphere that may have existed when Mars was still a blue world. Mars' atmosphere is thin, composed mostly of carbon dioxide, with less than 1% of Earth's pressure. This atmospheric thinness means the planet cannot effectively retain solar heat, resulting in temperature fluctuations that can range from 20 degrees Celsius at midday to below 80 degrees below zero at night. Furthermore, the absence of an ozone layer allows ultraviolet radiation to sterilize the surface. But hope lies beneath the surface. Radar data suggests the existence of ice deposits and possibly saltwater lakes under the polar ice caps and in underground caves. Lava tubes, formed by ancient volcanic activity, are seen as ideal refuges for future human missions and the search for microbial life. In these natural structures, radiation is blocked and the temperature is much more stable. The idea that life may have retreated underground as the surface became uninhabitable is one of the strongest hypotheses in modern astrobiology. Exploring these caves will require a new generation of robots capable of navigating complex three-dimensional terrains far from direct communication with Earth. The paradox of Mars is that, although it appears dead, it exhibits signs of seasonal changes. Clouds of dry ice and water form in its atmosphere, and dust storms can grow to envelop the entire planet for months. Small flows of material observed on slopes suggest active processes that we do not yet fully understand. Mars is a world in transition, a lesson in how a planet's size dictates its geological and atmospheric longevity. Being smaller than Earth, its core cooled faster, shutting down its magnetic dynamo and leaving it unprotected against erosion from the solar wind. The journey of exploring these worlds shows us that Earth is a temporary exception or a rare pattern. The study of Venus and Mars is not just about distant planets, it's about understanding the boundaries of life. If we discover that life arose independently on Mars, even if it became extinct, this would change our perception of the universe. It would mean that life is a common process, arising whenever minimum conditions are met. If, on the other hand, Mars and Venus have always been barren, despite their humid pasts, the uniqueness of Earth becomes even more profound and enigmatic. Current and future missions, such as the Europa Clipper mission that will investigate Jupiter's icy moon, or Dragonfly that will fly through the dense clouds of Titan, continue this search for habitability in unexpected places. The solar system reveals itself as a mosaic of worlds, each with a different solution to the enigma of existence. Technology now allows us to touch these soils, analyze their chemistry, and look to the past through geology. We are on the verge of answering whether biology is a universal planetary phenomenon or a singular accident of our pale blue dot. The interconnectedness of all these celestial bodies is evident. The water we drink today may have been delivered by comets from the colder regions of the system during the late heavy bombardment. The energy that powers our civilization comes from a star that is in the middle of its stable life. Understanding the solar system is understanding our cosmic lineage. Each planet, each moon, and each asteroid holds a piece of the puzzle that explains why we are here and where we can go. Space exploration is the tool we use to decipher this story, transforming points of light in the sky into tangible worlds, rich in detail and full of secrets waiting to be revealed. The complexity of the atmospheres, the violence of the impacts, the slow evolution of planetary cores, and the gravitational dance that keeps everything in order make up the narrative of our neighborhood. As we move forward, the distinction between Earth science and planetary science disappears. We become galactic geologists, solar meteorologists, and historians of deep time. The challenge of Mars and the warning of Venus remain the two pillars that frame our current understanding of what it means to be a living planet in a vast and indifferent universe. Humanity's persistence in sending machines to these extreme places reflects our innate need to explore. We are not content to merely observe. We want to measure, touch, and eventually inhabit. The colonization of other worlds, beginning with the Moon and then Mars, is seen by many as the next logical step in our evolution. However, this step requires that we first understand the lessons these worlds offer us. Venus teaches us about climate, Mars teaches us about history, and both remind us that stability is a privilege, not a right guaranteed by physics. With each new high-definition image sent by our robots, the distance between us and the other planets diminishes. Mars is no longer a god of war, but a desert of siliceous sands and pink skies. Venus is no longer just the goddess of beauty, but a furnace of acidic clouds. This demystification does not diminish the wonder. On the contrary, it deepens it. True beauty resides in the complexity of natural processes, in the elegance of orbits, and in the resilience of matter which, under the right conditions, organizes itself to question its own origin. Antithesis. Given the vastness of the solar system and the realization that worlds like Venus and Mars fail to sustain complex life, a question arises that echoes through the corridors of astrophysics and philosophy. If planets with characteristics so close to Earth's are common in the early stages of their formation, why is the cosmic silence so absolute? This question leads us to the concept of the Great Filter, a theoretical barrier that suggests the existence of a stage in the evolution of life that is extremely difficult to overcome. Observing the scars of Mars and the suffocating atmosphere of Venus, we begin to consider that the fate of these worlds was not an isolated accident, but perhaps the result of planetary laws that favor long-term stability. The search for extraterrestrial intelligence and the analysis of planetary habitability collide in a paradox. On the one hand, the laws of physics and chemistry are universal. On the other, the persistence of ideal conditions for biology seems to be a statistical anomaly. Venus and Mars serve as two sides of a cautionary coin. One represents excess energy and gas retention, the other heat loss and atmospheric protection. If the Great Filter is behind us, Earth is a miracle of survival. If it is ahead of us, the end of habitability in our neighbors may be the harbinger of our own technological or biological future. The transition from simple life to complex life, and subsequently to civilizations capable of signaling their presence through space, requires billions of years of uninterrupted climatic stability. Mars had water, but not time. Venus had size, but lacked the proper carbon recycling mechanism. Earth, through a series of geological coincidences, including the presence of a large moon that stabilizes its axial tilt and a robust magnetic field, managed to keep the thread of life intact. However, when we study the history of these planets, we realize that the boundary between an organic garden and a mineral desert is much narrower than we would like to admit. The discussion about Earth's rarity gains strength when we analyze the protection that the outer system offers us. Jupiter and Saturn, with their colossal masses, are not just gas and ice giants. They are the gravitational guardians that shaped the environment where life could flourish. Without Jupiter's influence to clear the inner system of massive space debris, the frequency of catastrophic impacts on Earth could have prevented any evolution beyond single-celled microorganisms. The architecture of the solar system seems to have been designed by a series of chance events that created a zone of calm amidst the cosmic storm. However, this same architecture that protected us also sealed the fate of others. The migration of gas giants during the system's infancy launched asteroids and comets on collision courses that forever altered the surfaces of Mercury, Venus, Earth, and Mars. While Earth recovered, transforming the bombardment into a source of water and minerals, Mars lost its regenerative capacity as its core cooled. The disruption of the Martian magnetic field was the turning point. Without the shield against the solar wind, the atmosphere was stripped away particle by particle, transforming a potentially vibrant world into a frozen relic. The antithesis here is clear. Habitability is not a static state, but a dynamic and precarious equilibrium. The concept of the habitable zone, the distance from the star where liquid water can exist, is often simplistic. It does not take into account the evolution of the star, nor the internal dynamics of the planet. Venus is technically close to the inner edge of this zone, and Mars to the outer edge. Both failed for reasons that go beyond their spatial location. This forces us to reassess the search for exoplanets. Finding an Earth too. So in terms of mass and distance, may not be enough if the planet does not possess a magnetic field or active geology. The exploration of Jupiter's and Saturn's moons brings a new element to this discussion. Europa, Enceladus, and Titan are worlds that defy traditional solar logic. Far from the sun's heat, they find energy through gravitational tidal forces. Oceans of liquid water, hidden beneath icy crusts, represent an alternative form of habitability, one that doesn't depend on an atmosphere. But even in these places, life, if it exists, would be trapped under kilometers of frozen shielding, unable to develop technology or observe the universe above. Cosmic silence persists perhaps because complex life requires not only water, but a surface exposed to a clear sky and a stable atmosphere for years. When we confront the fates of our neighbors, we are led to question whether humanity is alone, not for lack of life in the universe, but for lack of time for that life to become conscious. The great filter may simply be the inherent instability of planetary systems. Asteroids, nearby supernovas, climatic instabilities, and stellar evolution itself are constant obstacles. The history of Mars and Venus suggests that most planets that begin with biological potential end up losing the race against entropy before a civilization can emerge. This perspective profoundly alters our motivation for space exploration. If Earth is such a rare exception, the preservation of our environment becomes a cosmic duty. However, the same science that alerts us to Earth's fragility offers us the tools to try to overcome the fate that has befallen our neighbors. Colonizing Mars or establishing bases on the Moon is not merely a matter of curiosity, but an attempt to place the eggs of consciousness in more than one planetary basket. We are trying to outwit the great filter, extending our presence beyond the borders of a single world. The study of lunar and Martian rocks, the analysis of the chemistry of exoplanet atmospheres, and the constant monitoring of the Sun form a surveillance network that allows us to understand the risks. We have learned that the solar system is a place of slow but inevitable changes. Earth has an expiration date, dictated by the evolution of the Sun. In a few 100 million years, solar brightness will increase enough to trigger on Earth the same process that destroyed Venus. Earth's ocean will boil, and life as we know it will cease to exist. We are passengers on a ship that, although magnificent, has a final destination determined by the laws of physics. What sets us apart from Mars and Venus is our capacity to understand this destiny and act upon it. Space exploration is our response to the silence of the cosmos. It is an attempt to ensure that the history of consciousness does not end like the dry basins of Mars or the scorched plains of Venus. Every probe that traverses space, every telescope that peers into the darkness, is a manifesto against extinction. We are searching not only for other beings, but for a way to ensure that we ourselves continue to exist. The narrative of the solar system, therefore, ceases to be merely a description of planets and orbits and becomes a lesson on the survival of intelligence. The antithesis shows us that the universe is not a hospitable place waiting to be filled, but a rigorous environment where life is the exception. The silence of Mars and the heat of Venus are constant reminders that stability is a rare gift. As we look to the stars, we seek not only new worlds, but a deeper understanding of our own place in the chronology of time. The journey through the system's boundaries, from the heat of Mercury to the abyssal cold of Pluto and beyond, reveals a landscape of extreme diversity. But it is in the contrast between the three central rocky worlds that we find the essence of our quest. Where there is water, there may be history. Where there is fire, there is warning. And where there is life, there is the responsibility to understand both. The exploration of the solar system is the greatest intellectual adventure of our species, for in it we discover that we are the voice of the universe, attempting to narrate its own trajectory through chaos and time. Through the eyes of robots and the minds of scientists, we have transformed the solar system from a collection of luminous points into a map of possibilities and warnings. Comparative geology teaches us that every detail matters. The planet's mass, its distance from the star, the presence of a satellite, the composition of its core. Everything converges on the present moment, where a species rises to look back and ask, why here? And more importantly, for how long? The answers remain hidden beneath the sands of Mars and the clouds of Venus, waiting for our perseverance and technology to bring them to the light of consciousness. Space exploration is ultimately an act of hope. It is the belief that, despite statistical probabilities and planetary filters, consciousness can find a way to permanence. By studying dead worlds, we learn to value the living world, and by planning journeys beyond our atmosphere, we are writing the next chapter of a story that began in a cloud of dust and gas 4 billion years ago, a story that now, for the first time, has a narrator capable of imagining the future. Synthesis. The reconciliation between the icy desert of Mars and the suffocating furnace of Venus lies not only in observing their flaws, but in understanding that life and geology are parts of a single integrated system. The synthesis that emerges from our space exploration is that habitability is a biological process as much as a geophysical one. When we look at Earth, we realize that it is not just a stage where life happens, but a world actively shaped by biology to remain habitable. This perception shifts the focus of our search. We are not only looking for planets that have water, but for systems that possess the capacity for self-regulation. The solar system, in its maturity, reveals itself as a laboratory of divergent results that share the same origin. The organic matter found in meteorites and the presence of ice in polar craters on Mercury and the Moon indicate that the fundamental ingredients are scattered everywhere. The difference between a dead world and a living world may lie in the ability to maintain feedback loops that prevent the extremes observed in our neighbors. Mars lost its atmosphere because it did not have enough mass to retain its internal heat and consequently its magnetic shield. Venus lost its equilibrium because it lacked an efficient mechanism to bury carbon back into the rocks. Modern astrobiology suggests that life may be the long-term stabilizing factor for a planet. On Earth, microorganisms and plants regulate atmospheric composition, influencing the greenhouse effect and maintaining temperatures within a range that has allowed for the existence of liquid water for billions of years. If life had arisen and established itself on Mars or Venus with the same intensity, perhaps the fate of these worlds would have been different. The exploration of these planets forces us to see biology not as a final accident in a planet's history, but as a first-order geological force. Exploring the boundaries of the system through probes that now reach interstellar space, such as the Voyager spacecraft, gives us an external perspective on this dynamic. By crossing the heliopause, these machines show us that the solar system is a bubble of solar influence protecting a set of worlds from the interstellar environment. Within this bubble, diversity is the rule. Titan, Saturn's largest moon, offers an intriguing synthesis, a world with a dense atmosphere and liquid cycles on its surface, but where water is replaced by methane and ethane due to extremely low temperatures. Titan is a planetary-scale laboratory of prebiotic chemistry. It shows us that organic complexity can occur in environments that look nothing like Earth. If we find life forms on Titan that use hydrocarbons as a solvent instead of water, our definition of life and habitable zone will have to be completely rewritten. The synthesis here is the expansion of the possible. We are no longer limited to the rocky planet with water model. We are learning that the universe has multiple pathways for the organization of matter. The geology of worlds like Enceladus, which spews jets of water vapor and ice grains into space from a subsurface ocean, confirms that internal heat can come from non-neurogenic sources, such as tidal friction. This means that moons orbiting gas giants may be more likely to harbor life than planets orbiting small unstable stars. The architecture of the outer solar system, with its giants and their array of active moons, suggests that life may be far more common in the subsurface of icy worlds than on the surface of rocky worlds. This paradigm shift leads us to reassess the importance of sample return missions. Bringing back rocks from Mars or dust from a comet is not just an engineering feat, but a necessity for the ultimate synthesis. We need to compare the chemistries of different worlds in terrestrial laboratories to understand the variations of cosmic alchemy. What we have learned from asteroid dust like Bennu or Ryugu is that the building blocks of life were already present even before Earth solidified. Life is not an intruder in the system. It is an intrinsic consequence of its original composition. The synthesis between what we know about Earth and what we discover in space points to a growing responsibility. The technology that allows us to observe the birth of stars in distant galaxies is the same technology that alerts us to the risks of asteroid impacts in our own backyard. Monitoring near-Earth objects is a practical application of astronomy that can determine the survival of our species. We have learned from the craters on the Moon that space bombardment is a constant reality, and that the period of calm we are experiencing today is a window of opportunity that should not be wasted. The knowledge gained about the Sun is another pillar of this synthesis. Understanding the 11-year solar cycle and the physics of geomagnetic storms is vital to protecting the technological infrastructure that sustains modern society. The Sun, while a source of life, is also a source of risk. The synthesis here is the integration of space weather with our daily lives. We no longer live only on the surface of the Earth. We live in the extended atmosphere of a variable star. Space exploration also offers us an emotional and philosophical synthesis. The panoramic view effect, reported by astronauts when observing Earth from space, removes the artificial boundaries created by politics and culture, revealing the biological unity of the planet. This perception is the ultimate synthesis of our journey, the understanding that we are all crew members of a small spaceship navigating through the void. The fragility of Mars and the hostility of Venus reinforce the idea that preserving Earth is the only logical path for the short and medium term. However, the synthesis doesn't stop at preservation. It advances to expansion. The idea of terraforming, though still in the realm of theory and fiction, is the logical conclusion of our understanding of planetary engineering. If we understand why Venus warmed and Mars cooled, we could, in theory, reverse these processes or create new environments on barren worlds. Humanity is moving from being an observer of the system to a force that can eventually shape the destinies of other worlds. The history and exploration of the solar system reveal a dynamic, interconnected system full of lessons. We move from the thesis of common habitability to the antithesis of rarity and isolation, only to arrive at the synthesis of life as a resilient phenomenon that seeks its way through time and space. Our cosmic neighborhood is a mirror where we see our past, our present, and the various versions of our possible future. As we conclude this phase of exploration, we realize that each mission, each piece of data, and each image brings us closer to a deeper understanding of reality. The solar system is not just a place in space, it is a chronology of matter becoming conscious. The journey through the limits of the sun, from the inner planets to the outer giants, is the journey of human self-discovery. What we find out there teaches us more about who we are inside, reinforcing the inseparable link between stardust and the thought that observes it. The complexity of orbits, the chemistry of atmospheres, and the geology of planetary cores form a cosmic music that we are only beginning to hear. The final synthesis is the harmony between technical knowledge and awe of the vastness. We are ready for the next steps, armed with the lessons of Venus, the warnings of Mars, and the inspiration that Earth provides us. Continuous exploration, for the universe is vast, and our curiosity is, by definition, infinite. Conclusion. The journey that began in the dust of a primordial nebula and took us through the furnaces of Venus and the deserts of Mars now reaches its final point of reflection. Looking at the solar system, not as a collection of isolated objects, but as a narrative of survival and transformation, we are confronted with our own position on the timescale. Space exploration, far from being merely a search for new resources or territories, has proven to be a profound exercise in self-knowledge. We have learned that habitability is a rare gift, and that the boundary between a vibrant world and a barren relic is maintained by extremely delicate physical and chemical balances. In this panoramic view, the solar system ceases to be a map of distances and becomes a map of destinies. Venus reminds us of the destructive power of an out-of-control atmosphere. Mars shows us the silence of a world that has lost its geological breath. Earth, positioned between these two extremes, emerges as the conciliatory factor, where mass, distance, and biological luck converge to create a conscious anomaly. The contradiction between the abundance of ingredients for life and the absolute silence of our neighbors suggests that intelligence is not a guaranteed outcome, but an achievement against all the statistical odds of the cosmos. To re-enter the context of our system is to understand that we live in a period of exceptional stability within a history of chaos. The themes of thesis and antithesis, the suffocating heat and the deadly cold, find their synthesis in our capacity to observe and learn from these lessons. The conciliatory factor is science itself, which transforms distant light into data and mystery into knowledge, allowing us to predict the future through the study of others' past. We are on the threshold of deciding whether we will be passive passengers in this system or whether we will assume the role of guardians of consciousness in our stellar neighborhood. The connection between the main theme of exploration and the destinies of Venus, Earth, and Mars reveals a fundamental truth. Life needs time as much as it needs space. The final explanation of this link shows that humanity is the first phenomenon in the solar system capable of understanding the mechanics of its own cradle. If Venus is the failed past, and Mars is the dried-up future, Earth is the present that needs to be preserved and expanded. The pattern break in our understanding occurs when we realize that we are not just looking at planets, but at alternative versions of ourselves, mirrored in rock and gas under the light of the same star. This grand perception elevates astronomy from a technical discipline to an existential imperative. The explanation of the contradictions between the beauty of the cosmos and its indifference to life highlights the importance of each step we take outside our world. The silence of Mars is not merely the absence of sound, but the absence of a narrative that we now have the opportunity to restart. The cliffhanger of this story lies in the last gap in understanding. Whether life on Earth is the beginning of a biological diaspora that will fill the system, or whether we are merely the last glow of a candle that goes out in a universe that prefers mineral rest. The breath that space offers us is the opportunity to change this outcome. The final word in this great investigation is responsibility. The ultimate resolution that reconciles all planetary paradoxes is that habitability is not a state, but a task. By tying together the content of this journey, we close the loop opened at the beginning. The atoms that once floated in the protosolar cloud have now organized themselves into neural systems capable of questioning their own origin. The logical reconnection of all points shows that the exploration of Mars or the study of Venus are, in fact, ways of protecting our own home. There is no real separation between Earth and the rest of the system. We are an integral part of the same celestial mechanics. Human consciousness is the tool through which the universe finally sees and understands itself. The final deliverable of this script is the realization that our long-term survival requires us to become a multiplanetary species. Not out of disdain for Earth, but out of respect for the rarity of life. The conclusion of this narrative loop brings us back to the pale blue dot, but now with a transformed vision. The knowledge of the difficulties faced by our neighbors makes our world even more precious and our mission even clearer. The exploration of the solar system is the greatest testament to human perseverance. From Galileo's first observations to the rovers that are now drilling into the Martian soil, our trajectory is marked by a refusal to accept the unknown as insurmountable. This is the resolution of our paradoxes. We are small in scale, but vast in understanding. The fate that befell Venus and Mars serves as a map of what to avoid, while our technology and curiosity serve as the fuel for what we can achieve. The history of the system is still being written, and we are the authors of its next chapters. We conclude this analysis with the certainty that the silence of the cosmos is not a void, but an invitation. The lessons of geology, atmosphere, and stellar evolution converge on a single point of decision. The solar system offered us the cradle and the raw materials. It is now up to us to build the bridges that will ensure that the light of consciousness does not go out when the sun inevitably changes. The synthesis of all that we have learned is that life is the way in which the universe avoids entropy, and our journey is the ultimate expression of this resistance. In this vast expanse of galaxies and particles, our history is a brief but intense flash. The preservation of the pale blue dot and the exploration of the red deserts and acidic clouds are parts of the same struggle for survival. We look to the sky not with fear, but with the recognition that our past and our future lie there. The solar system is our domain, our laboratory, and ultimately our greatest adventure. May the clarity of this understanding guide our next steps among the stars, for the journey to comprehend the infinite is only just beginning.